Okay. So as we look at this activity, all right, now that that's gone, let's take a look at this and let's start asking ourselves a couple questions. Okay. Now we have two types of random variables: a binomial and geometric. Now within both of those, we're going to talk over those throughout the course of the next couple of days. The one we're going to talk about though is binomial right now. Okay. We'll talk about the differences there. Now, question. This is just a conversation piece for us. Is this a random variable, what we just did?
Yes.
No.
Okay, why, Campbell?
Just feel like it is.
Well, hopefully it was
We
random.
drew random.
Some of you may have,
Yeah.
some of us maybe have picked out 3 yellows, right? And in that case, it would not be. But in this specific situation, when I tell my wife, hey, you don't need to be taking 7 reds out, right? Affecting the amount of reds that I can get. Now you have to choose them at random. In this case, we will then have a actual random variable. Now, watch this. This may or may not be our actual probability, and that's what we're going to look at. But in total, we had 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? There are 20 tick marks? We'll just go with it, okay? 20 total, right? Do this for me. Morgan, would you mind throwing these in the calculator real quick? Or just someone? That's fine. Let's find the probability of each. What was the probability that you got 0 out of 7 possible reds? You got only 0. 3 over 20, which would be 0.15. Well, I guess out of 20 we're good, right? What about 6? What would that be? 0.30. This one's 6, which would be? Or no, is that 0.25? 3, 4, 5. Or no?
What?
1/4, that's 0.25, right?
6.
What?
This is 5 right here.
Oh, it's 5.
Yeah, my fault. I misread that.
Yeah.
0.25, what about 6?
0.30.
0.30, what about 4?
0.22.
0.2 and 2.
1.
0.1. What do all of these add up to equal?
1.
Good.
Yeah.
Alright, question. What do we call this? Probability distribution. Is this what type of
Two-way chart.
random variable do we have other than what we talked about here? What type are we going to use? Discrete. Good, because it has
How many you got in there?
because it has gaps. Very good. Good job, Matthew. So when we talk over this, when we talk about a random variable, we have 2 different kinds. Today, we're going to talk about binomial, and in actuality, this right here was a binomial, and I'll show you why in a second. Okay, so question. Here we go. Is this, meaning this chart, probability distribution, is this the true probability?
No. There's 16
Okay,
of
Mary
us.
Martha, say it again.
There's 16 of us in here.
Were there 16?
There's 16 students. But there's
So
16
someone maybe did it twice or something? Possibly. Okay, that's true. What is the true probability?
1/4.
Martha did it twice.
I think twice.
Okay, 1/4 of all of my starbursts are red, correct? Or 0.25, right?
Yeah.
So when we think about the true probability,
Yeah, point-
really what we're saying is that what?
25%.
That's not going to equal the expected value.
Good. How can we get closer to our true probability? This was just our sample, right?
Yeah.
How can we get this equal to my, or closer to my true probability?
More
trials.
Okay, say this one more time.
More trials.
More trials, I like that. What happens to the sample size?
Increase it.
Good. When I increase the sample size, this gets closer and closer to my true probability. We remember this, right? Because if I came and I shot free throws, and I shot 5, right? Guys, you good? Matthew, you good? Okay, I just want to make sure. When I shoot free throws and I shoot, let's say, 10 of them, and I get 5 out of 10, does that mean I'm a 50% free throw shooter?
I mean,
I hope not, right? I hope not. Maybe right now because I haven't shot in a while. But let's say I shot 1,000 of them, and in that case, let's say I hit 500 out of 1,000. Is that reason to believe that I'm closer to a 50%
Yeah.
free throw shooter?
Yep.
Yeah, because what did I do to the sample size?
You
I increased it. So in this, we could probably do a little bit better if we increased our sample size from maybe 7 to a higher number, right? That would be probably give us a better one, but we'll take it and we'll go with it, okay? We talked about this. All right, question. What would you expect to be the true mean? of this probability distribution?
Whatever 0.25 times
Yeah.
7 is.
Say that one more time, Matthew.
Whatever 0.25 times 7 is.
Okay, someone throw that down. What's 0.25 times 7? What's the expected mean? 1.75, okay. So we could say approximately, over the course of time, that my wife will get about 1.75 if she kept doing this over and over and over again. And so I'd say that that's pretty fair, don't you think? That she gets about 1 to 2 reds per time instead of taking all the reds all the time, okay? Now, there's a couple of tests that we have, and this is what we're going to go into. This is where the activity kind of launches into, and this is the big concept, all right? So y'all have your notes out. We're going to hop right into it. We're going to roll to it today. All right, so this right here is our starburst here. Does anyone love starburst? I'm just curious.
Oh, yeah.
Love
More of a
starburst.
chocolate, yeah.
Yeah, Mr. Washington.
I know you are.
Mr. Washington, what's your favorite color?
Red.
Red?
Yeah.
Gotcha.
Yeah.
Anyone like orange?
That's a good one. Orange is
Orange is the best.
Wow.
You
I like
kidding?
orange.
all right.
Why? Just plain.
Okay, so as we go into this, here's what we're focused on, okay? Now this is important. This may not seem important right now, but as we launch into tomorrow, it's going to really be important because of the difference between the two types of rated variables. This is again called what? What type of rated variable are we talking about today? It's a discrete that we're talking about, but specifically, it's a binomial, okay? It's a binomial. Now, in order to have a binomial, to decipher between it, in order to use this binomial random variable, we have to have 4 things. We call this bins, okay? Bins. Now, the first one, the B stands for binary. Can someone just, knowing just words in general, what's binary?
2 things.
2, yep, 2 things. I like that.
James.
And we have either what or what.
True or false?
True or false, we call that success or failures, right? Success or failures. So each observation falls into one of just 2 categories, which we call either a success or a failure. I was trying to think about this morning. Success does not necessarily mean like awesome. Success does not mean awesome. Could someone explain to me what that means?
It means that something is true, like for example, having a disease, that's true.
It could be a bad thing.
Actually, that's probably better than what I would have said earlier. That's good. Yeah, that's a great example. So because of that, like if we're doing an experiment, success means that maybe you got the disease or whatever, right? That's going on. That doesn't mean it's an awesome thing. That just means success means that it happened, right? Whatever we're studying at that given time. Great job. Wes, good work there. Independent, and observations are all independent. Meaning, what does that mean again? Oh, I love it.
They do not, one does
I love
not
it.
affect the other.
Yeah. One observation or one result is not impacted by another, right? One is not impacted by another. Oh man, this is where it gets really good. Question, is this binary what we just did, this experiment? Yes, it does. The success of selecting Mr. Washington's favorite red starburst compared to not selecting that, right? That's binary, success versus failure. However, question, is this independent?
No.
Maddie, explain.
Because if you're pulling out, if you have a bag of 7,
Yes, ma'am.
and then you pull out a red, and then you're trying to get a yellow, or you're trying to get another red, and you will only have 6 left, so it'll be higher.
Ooh, is she right?
Yeah.
Yes, so is this actually a binomial? It actually is. This is where I throw a little curveball to you.
That's
Because
the
you're
problem.
picking
You try
7
is
at a
better not
time.
that.
Yeah,
Each 7
And then
drops,
put them
you do
back.
one after.
what Maddie said was right, and this is where you kind of have to look into it. And Matthew, I hear what you're saying. This is just something we got to know. How many starbursts are there?
4 times.
A ton. When I select 7, if I select a red one first, right, which is possible, it does impact what I would get the second time. Does that make sense? Because I've already selected a red. However, how small is the change?
Not much.
And it's not much because of the fact that there's so many of them, right? Now, that will be more clear, especially on an AP exam. But for this one, I would say that it wouldn't be independent, but it's still, we're going to count it because the probability that it impacted was very, very small, okay? You'll see that as we keep going. Does that make sense? So, Maddie, you're correct, but we're going to keep going. We're going to still say that it follows that binomial based upon this here.
Could it also be because you're just reaching in and taking like 7 at a time and then putting 7 back in, like for the next person to draw? Like you're just grabbing 7.
That's a
You're
good
not
question.
grabbing them one by one.
I think that's what Matthew was saying, right?
I was saying like since you're replacing them after you, it's like I go and I pick 7, but I'm putting all of them back. So the number of reds that I get doesn't impact the number of reds that he gets because I put
Right,
them back.
yeah.
True.
So that's why
True,
like
true.
my result was independent from his.
Yes, that's true. Now,
The
if I
result
didn't,
of
if I
picking
held on to those 7, that would in that case
Right.
negate that, right? That's a good
But you're
question.
not picking like one by one.
True.
And you're just reaching in and grabbing 7.
That's true.
Yeah.
So I would say by either of those two, right? I would say, yeah, you're both exactly right. You know what I'm saying? Does that make sense? Awesome. Very good. Number. This is the next one. There's a fixed number n. What does n represent again?
Populations.
Yeah, n represents, I want to get the wording right. It's our trials. How many trials did we, or observations, how many observations did we have?
In the class.
Yeah, it's exactly right. If I just said to my wife, hey, you could choose as many as you want, would that be binomial then? Instead of giving her like a limit of, hey, you got to just choose 7 at that point. No, it would negate that, right? There wouldn't be a set number of trials or observations. Trials or, my fault, observations. So it's got to have an n. That's the bins, the n in bins. Success. This is our S. The probability of success P is blank for each trial. What would that be? It is independent, but it must be the same for each trial. Got me? It's got to be the same for each trial. What was the probability for this one? 1/4, right? And again, it's approximate. I didn't go through and count all those. I know you're disappointed in that, but it was approximately 1/4. All right? Excellent. All right, so let's keep going. Now, this is where we're just going to hop into this, and we're going to have you actually do this together and see, does it follow our bins, right? Binary, independent, number, and successes. The distribution of the count x of successes in the binomial setting is the binomial distribution, okay? That's what we call it, all right? It's called the binomial distribution. You write that there? With parameters blank and blank. Anybody read?
0 to 1.
0 and 1. Ooh.
No read, not even read.
Is that your final answer?
Yes.
No, N and P.
I was
Good.
close, yeah.
N represents what?
The trial.
The trials. P represents the probability. Nicely done. Okay. So again, parameter N is, and I like to just put it down to get the official number of trials. And again, the parameter P is the probability of success. Okay, that's important. The probability of success. What's the probability of fail in our experiment, or in our
7.5.
0.75 or 3/4? Right. Good. 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 All right. The possible values for x are what? What are the values we could get for x? Ooh, Yeah, I would say you're exactly right. It's numbers 0 through what here? Yeah. So numbers 0 to, and this is 7, but we'll just say to n because it could be different, right? Sometimes we might have 10, we might have 15. That could change there. All right. An abbreviation for binomial random variable for x. We'll write that in as this. Remember when we did the n, which is the normal distribution? We did n that looked like this, right? And when we did n, we did like our standard deviation. Oh, I'm sorry, our mean and then standard deviation, right? This is very similar, except we're going to say b, the binomial of n comma p, which is the number of trials and the probability for each trial.
What is B?
Okay? B stands for binomial. Okay? Which what satisfies binomial? It's got to be random and it's got to follow bins. Nicely done. Okay? Now here's what I want you to do. In your groups, you may not get this perfect, but I want you to start thinking in that. I want you to go from numbers 1, 2, 3, and 4, and I want you to execute and see whether this follows a binomial distribution by saying, okay, is it binomial? Is it independent? Does it have a set number of trials? And is there the same probability of success each time? All right. If it fails at one of those, you cannot use binomial distribution or use a binomial with the random variables that are there. Does that make sense? So what I want you to do is I want to get just a couple minutes to see if you can go through each one, and then we'll go over them together. Sound good? I'm going to give you 3 minutes, 5 minutes, 5 minutes. Ready? And go. See if you can talk it through with those around you.
Alright, guys.
Is it hot in here?
Yeah, I think it's just you, Coach Jay.
Jeez.
Is you know, take a step out of the room.
Oh,
Yeah.
is that what it is?
Yeah.
I trust you, all right.
Alright, can't be worse than 56. 20 children born. Go ahead over there. I think it's Ooh. James doesn't get a vote. Say it again.
See if we can
You are.
test it.
I know.
Saving a yellow for later.
Different notes.
My favorite
No,
too.
don't.
James, you have different notes than me. James, you have different notes than me. Oops. Don't say it. Don't say it.
Or
If it's not there, tell me why it is not. Okay?
Additional instructions for
Yeah, I wanted to be success rates.
Yeah. Yeah, they're gonna keep going.
Mm-hmm. Yes, ma'am. Come on.
What do you mean by saying?
Yeah. James, you think two's yes? Sorry.
Oh, okay.
You're
So in
wrong.
order for it to be a binomial random variable, it has to follow the B, I, and an S. Okay? So it must be binomial. It must have a success or failure. It must be independent. That's the I. Okay? And there has to be a set number of trials. Right? For us, we did 7. Right? Set number of trials. And S stands for the probability of success has to be the same throughout. Does that make sense? Good question. Yeah, there were 20 of us that did it, but the trial, every time I pull one of these, that's a trial. 2, you know what I'm saying? 3, 4, how much did I get? 7, right? 5, 6, and 7, right? This is mine. So every time that I do this, right, I've got my wife, when she chooses 7, these are 7, this is one representation, there are 7 total trials, right? Because each of these has a 1 in 4 chance of being one of these, right? Now what we did is we did 20 of these. Right, so each of you did 7 trials that are there. Does that make sense? Here's maybe this will help you. One of these, this is 1 C. Each of these are a trial. So there's 7 total trials.
But we have 25.
Exactly. We replicated it 20 times. Does that help you? That's a good question. That's a really good question. All right, are we good? All right, let's see it. Here we go. Hand out some tickets. I got tickets galore. Here we go. 20 children. You observe the sex born at a local hospital. X is the number of girls among them. Gabby, what'd you say on this one? You said yes? Y'all agree?
Yeah. Yes.
Yes, it is. Why did you say no, Matthew? Or who? Did someone say no? Oh, okay, never mind. I'm hearing stuff. Must have been my imaginary friend. All right. Number 2.
Your elf friend?
All right, Morgan, why is it no?
Because there is not a fixed number of trials.
Good, not a fixed number of trials. I tell you what, I'm gonna give one to Emily too. She had asked a question which was really good, and I want to make sure I say this. How many trials over here do I have? I want to be careful on that. We replicated it 20 times, but there are 7 trials. Does that make sense? 7 trials. So each set of 7 is a sample that I took, right? So there are 20 samples, but in this, each one that I selected, got me, represents a trial. There are 7 total trials. Does that help y'all? Just be sure of that. Max, you good, my man? Okay, right on. All right, number 3, Max. What'd you say on 3?
I would say no.
What was wrong with that?
Well, it's like not independent, or it might not be independent because he gets some extra help on that.
Good, because it's not independent. Because what happened if I got it right or wrong?
It helped you.
It helped
Gave
you.
you instructions.
Good, it gave you instructions which impacted. So does that mean that it can be independent, Sermon?
Shoot.
It can't be, right? That means it's not. It's not independent of each other. Very good. Number 4, this is a tough one. This is one we want to really go in on. Maddie, what do you think?
Well, I originally put yes, but now I'm saying no because you just said that there was a sample of 20, not so. With a simple random sample of 8, that would count as 8 trials, right?
This is right here. 8 switches from a shipment of 10,000 switches.
So that's just a sample.
That would. How many trials did I take out of this? 8, correct?
8.
8, because I select an engineer chooses a simple random sample of 8 switches, right? Very similar to if I had 1,000 starbursts and I selected 7 starbursts. That would be very similar to what we just did. Does that make sense?
Yes.
So we would say that this was yes. Now, some of you may say, did anyone say that this was not independent? Because if I selected 1, it's very similar to what we were talking about earlier. So technically, because there's a 10,000, if I took 1 switch away, it would decrease that probability. Got me? But there's so many of them that it really doesn't impact it altogether that too bad. Okay? So we would say that's still yes, that it does satisfy the independent check there on the bins. Maddie?
So if it was 10 switches instead of 10,000, would it be no?
I would say no in that instance because now we're talking about a lot smaller number. And if I choose one of those, right, in that instance, because there's such a small amount, the probability changes, doesn't it? So I would say the probability changes as well as it's not independent.
But
Right.
we don't know if he's picking them all at the same time or not. Like, that's the thing. If he picks them all at the same time, the probability doesn't change. It's still the same that it was whenever he drew them.
That's what I want to look at because y'all brought up a good point. I would say that even in that instance, even if I chose them all together,
I don't think it matters.
I don't think the probability doesn't change if you pick them all together because
Well, it doesn't
you have
matter.
an
if you can have,
equally
like
likely
one.
pick. Yeah.
There's no difference. I don't
Or if you
think
could
go ahead, Matthew, what were you saying?
I was saying like with the starburst, I don't know if the probability. There's no difference if you pick them
If
all
you
at
pick
the
them all
same
at the
time.
same time, like all 7.
If you pick them all at 7 at the same time, or you pick just 7, like one at a time, you're still picking. I don't know if the probability changes that much. Like it changes like between each one, but I don't know. It's so random anyways, and I think the probability would be so small.
I agree. I don't think when we do this, it's going to be extremely evident, Maddie, of what's going on. I don't think that they would say out of 10 switches, and if it did, we'll talk about that as we approach this year. Normally, it's going to be out of a huge sample. We choose 8. In this case, we're calling this a huge sample because there's a lot of starbursts here. So when I choose 7, we're just going to call that is independent. You know, that does satisfy the independence that's there. Got me? What I select in 1 will not be impacted by what I select in my second one, whether I select them all together or one by one. Is that fair? Either way, we're good. We're good on that. Okay. Now, here we go. Now, I will tell you this right now. What I'm about ready to say is extremely important for what we're going to be going to, okay, where we're headed. Now, I will also tell you that this doesn't involve starbursts, so it's not like extremely like, oh my goodness, amazing, but we need to make sure we're still with this, all right? Still with it. So we're going to go through this fairly quickly and we'll rock and roll, okay? Now, with this, to find what our binomial probabilities are, to figure out what the chart would be in terms of the expected numbers, all right? I want to make sure we start with this. We start by having order does not matter, when order doesn't matter. And in this, we use a combination, some of you have done this before, to figure out the different possibilities that could be had within this, within a probability distribution, specifically within a binomial distribution, okay? Again, this will be called our binomial coefficient, and you'll see that in just a second. Now, I'm going to give this to you. This is going to look very confusing. Some of you understand this because you've done this before. Some of you may struggle on this, okay? And well, that's why we'll break it down, all right? Jerry, you good, my man? All right? Helping you out. All right, let's do this. N, C, K. Okay, what does N mean? The number of trials. What does K represent?
Oh,
This is good. if I said out of 7, what is the probability in the 7 trials that my wife will get 3 reds? On the
The probability is success.
Yes, probability of a specific success. So I could say, 3 or 4, right? That's what would go in for K. All right, and we'll look at that and again, example here in a second. We write that as N over K. You can see that on your calculator. The big thing is to see that, be familiar with that on a multiple choice question. Okay, Matthew, you with me?
K or NCK?
Say that again.
Which one for the multiple choice?
Both of these are the same thing.
I got you.
Okay, both of them are the
So
same.
is the NCK, is that the same thing as the probability of X equals K and then equals? Because that's what it says
Say that one more time again.
on our formula. The P of K equals X
P of K
equals,
equals X.
sorry, P of X equals K.
P of X equals K. Okay.
But it's like all inside the parentheses. So it's like P of X equals K, then close parentheses.
P of X equals K.
K, and then close
Close
it.
the parentheses.
Yeah, and then equals. That's what it does on my formula sheet. Is that the same thing as?
Could I look at that in just a second? I'm going to do this because I've got one more thing to add at the end, and then we could come back to this. Does that sound good?
Okay.
Because I may answer that question. So once we keep going, we got this. This is the formula that you find. N exclamation over K exclamation
Oh, not
over
the
N minus K
exclamation again.
exclamation. We've done this before.
Not the
Okay.
exclamation.
We've done this before. Now, here's what the cool thing is, all right? Now, hang tight with me. You're going to need to see this once because I just need to show it to you. You need to be familiar with it. Hear me out, though. We have a way to do this on our calculator. So you're saying, Coach, why in the heck do we have to do this? This is boring. I know it's boring. We just got to do it. The reason why is because on a multiple choice question, there are some that you actually have to see this, and the way they give the answer is in one of these forms. And that's why we got to do it. Sound good? We just got to do it. All right, so let's go. Let's keep going. Okay, let's look at these examples. All right? Now, if we roll a die 5 times, what is the number of 4s that can appear? So question, okay? Max, what is N in this?
Rolling dice 5 times.
5 times. Good. That would be 5 is our trial, right? Set trial. We got it. Do we have a set success rate?
Yes. 1 out of 6.
1 out of 6. Very good. So the P would be 1 out of 6. Very good. Nicely done. Okay? Now, here's what we're trying to find. What is the probability that X equals 1? Meaning that over the course of 5 times, what is the probability that I will roll a 4 1 time? Okay? That's what we're finding. Now, again, I'm going to show you. I'm gonna have us tomorrow do it on our calculator, and that's really the big part that I want you to focus on. But I need to show this to you so you've seen it once, all right? So here's how we do it. We say blank C what? 5C1, okay? All right, we could say in this example, we could also say if we put it in on our calculator, we could have this as 5-1, right? Because that's the same thing, right? Both are the same. Now, 5C1 stands for the coefficient that goes in front of the binomial, right? The coefficient's just the number without the variables. Y'all remember that? Okay? So we'll make sure. Now, with this isn't the only part that we have. How many times is the 4 going to be rolled?
1 4 or 1 6.
1 time, right? 1 time. So 1 out of what?
5.
1/6. I want 1 4, right? How many total rolls am I going to get? 5. So I have 1, 2, 3, 4. Let me get a different color because this will help us. 4 and 5, right? That means for one of these, I'm going to have a 1 in 6 chance because I want 1 4 to be rolled. That means on my 2nd, 3rd, 4th, and 5th, do I care whether I get a 2, 6, 5? I don't, right? I just can't get a 4. So that means that in this example, I'm going to have a 5 in 6 chance of rolling something other than a 4. So what I have is this right here on my right side, but that represents just 1, right? 1 different combination. That's why once I multiply this across, I have to multiply by the combinations of 5 choosing 1 to basically factor in all the other combinations that could come with this, okay? All right. questions.
Wait, this C means like combination of?
Correct. This right here, the 5C1, or you can write it as 5/1, right? You'll see that there. Meaning, I have 5 trials, I'm choosing one, or one time that it'll be, one time that I'll roll 4, right? Because x equals 1. That stands for the combinations, and everything to the right of this 1/6 represents the different options I have in terms of 1 and 6 rolling a 4, 5 of 6 of not rolling a 4, 5 of 6 of not, 5, 6 not, 5, 6 not. When I multiply that across, right, I will get a number that corresponds to 0.402.
Why'd you start doing not instead?
Alright.
Say that again, Max.
Like, why'd you start doing not rolling 6?
Yeah, good question. Because how many 4s do I want to roll? 1. So the 1 and 6, the blue one, represents one success. That's a success. That means the other 4 I have to fill in because I rolled it 5 times. That's my trial. That's why I represent this with 5 of 6 4 times. Got me?
So is that your probability that happens?
Correct. What is the probability, expected probability, that I will roll 1?
1, 4,
4.
and the rest doesn't matter what?
Does not
any
matter.
other number before.
Correct.
That's
Only
your
what I'm
probability
saying is only 1
40%.
4. Correct. Okay. Yes, Maddie.
That's
Okay.
it. Formula C.
Yeah, go
So
ahead.
is that the same thing as this formula right here? So we come out with the same answer?
That's exactly right.
Okay.
That's what you were
Oh,
asking?
is it?
Perfect. And I'm going to show you how or why that's the case. Is that cool? Yes, ma'am.
Why did you put that on your
It's not equal. This represents, if you threw this on your calculator, 5C1 on your calculator, you would get all the different combinations of rolling a 1 out of 5 specific trials. Or rolling a 4 out of 5 specific trials. Got me? This right here is just saying that this is one combination. That's why we've got to multiply by 5C1. The 5C1 tells me that order doesn't matter, right? Because it doesn't matter if I roll a 4 first, second, third, fourth, or fifth. It does not matter. All we need is to be able to say, oh, these are the different combinations. And as I look at these combinations, these are the possibilities where we have 1, 4, and the rest of these are not 4s. Does that make sense? Could I maybe do one more? Maybe that will help us.
Wait, that
I think I know
4.402,
Yes, ma'am.
is that, what is that? That's probably
That-
wrong one.
What is the probability that x equals 1? Meaning, what is the probability that a 4 is rolled only once out of all the trials of 5? Does that make sense? How did I get that?
Yeah, did you put that C on your calculator?
You will. Now, here's what I don't want to get in too much into, because what we're going to do is I'm going to show you a really easier way. I'm going to show you an easier way come tomorrow where this doesn't even have to be done. The reason why you have to see it is not to try to get this to equal this on your calculator. It's to recognize that, oh, when I have a trial that are 5 trials and the probability is this way, how can I put that in and recognize it on a multiple choice? Does that make sense?
So it's not just those fractions multiplied?
It's these fractions multiplied and then
With
finally
that.
multiplied by the combinations that you see at the end. Okay? Alright? Now, can I do one more? Because this, again, I understand. This is weird. I know it's a little weird. Okay? Do y'all have this one? Alright, watch this. Let's see if we can just do this one more time here. Okay?
Yeah.
Again, we have 5. We have 1, 6. What's the probability that x equals 2?
5C.
Okay? 5C2. Again, this represents all of the combinations of getting 2 4s when I have roll 5 times, right? Now, because of this, we have 5 specific rolls, right? How many times am I going to get a 4? 2, right? So this is going to be 1 of 6, 1 of 6, 5 of 6, 5 of 6, 5 of 6, okay? All right? And we'd multiply those together, and I'll just give it to you. It would equal 0.16. Now, there's an easier way to write this, and Mary, Martha, and Maddie, you both caught on to it, okay? On your formula sheet, it will show you this, okay? So you'll have this. But the easiest way of doing this is taking 5C2, okay? And I'm just going to rewrite this and just put it in an easier way. We'll put this as 5 over 2. Sorry, not that. Right there. 5 over 2. That means that the combination of 5 choose 2, okay? 5 choose 2 is multiplied by the probability of P, which what was the probability of P? 1/6. Okay? To the x power. How many x's did we have? 2, yeah. Okay? Let's see if I can move this here. I know, look at that, right? Ooh, look at that. Multiplied by 1 minus p. What's p again? 1/6. So what's 1 minus 1/6?
5/6.
5/6 to the, how did we get third?
You have 3 other
Five
variables.
minus
It would be n minus whatever my x was here, okay? Or in this case, k. So n minus k. So this would be a total of 3. Again, the 3 and the 2 must add up to be equal to your total number of trials, okay? All right? I know this is taking it's like a, I know it's a weird one. Again, recognition, that's all I need from you on this, okay? I don't need you to put this in, I just need recognition of, okay, I see how to recognize that on a multiple choice, okay? B, did you have something?
Why did you put the 5/2 with the 2 on it?
This one right here?
Yes.
This is the same right here as 5C2.
Oh yes, but you don't include it in the multiplication.
When you put this in on your calculator, this will give you all the different combinations. You might say, Coach, where did you get, what does that equal? When you put in your calculator, this is the formula that it calculates on your calculator. The different combinations. Now, do you need to know that? Memorize that? No, you don't. All you need to do is be able to recognize, okay? Recognize what that would look like. If I said, oh, here's this, and then I said, okay, tell me what the equation or what you would have to multiply to equal that, you're going to have an opportunity to use your calculator to get the actual number out in an easier way. I just need you to recognize this here, okay? Does that make sense? That's all we need. Mary Martha?
Where are the exclamation marks? Like, you don't have to worry about those? What is that?
This right, no, all I'm looking at is this 5/2.
How do we
Okay.
plug that into our calculator? I think is what she's asking. Would we just put 5/2?
The exclamation point, like everything.
All I
like
need, you will not need to do that on your calculator. You will not. Mary Martha, and B, this is the weird part for us, I know, is a lot of times I'm like, oh, this is how you plug it in, and all you need to do for this part is recognize that this right here, everything I wrote right here,
Oh, we don't even
That
have
is-
to calculate it. That's
No.
just like multiple choice questions.
yes,
Like,
yes,
what does the formula look like?
that's all you need to do,
Oh,
okay? In fact, I don't want you to do this on your, because then you'll have more opportunities to mess up. There's an easier way to do the actual number part. We'll do tomorrow. But I just need you to recognize this because there will be or could be one where you have to recognize it there. Sound good?
Yes.
Okay? All right, let's do this. Let's do this one real quick. Okay? Again, we got 6 minutes left, and then we can get this done. That way we don't have to do it tomorrow. Okay? All right, 80% free throw shooter shoots 5 free throws. Okay? All right, the number of makes. Is that us?
Yes.
All right, do this.
You know what that
I am. Hey, could you do this for me? Hey, y'all, real quick, because I'm going to get through this with the other class. Could y'all watch the last 5 minutes of this podcast tonight? Is that cool? Just watch the last 5 minutes, okay? I'm going to continue on this, and so just check it out, all right? Just check it out. Does that make sense?
yes.
It's a little weird. Oh, I know you had a question.
every day?
Okay, I got it.
Get it? The weird thing is, we don't have to know how to actually calculate it.
You made a 0 on a multiple choice quiz. That's how bad you are.
Let me know if I can help. All right, let's continue with this because I want to make sure that we go through this together. Appreciate y'all for bearing with me. This is not the most fun part right here, and I get that. We're going to have a better, easier time trying to do this tomorrow when we actually can solve these things. So we will go through that here in just a second, okay?
The Mason.
What time?
I think after school, but
Like right
I
after
haven't
school?
met them today.
Oh, okay.
Sure.
Dang it.
Back.
Just in case.
I wish another time. Yeah, I wish I
Is that cool?
Oh.
Sounds good. Hey, I love that though. Was there statistics on there? There was a little bit, wasn't it? Cool, man.
How you doing, Coach?
What's up, Brandon? Good to see you. Sorry, y'all. I'm just saying hey to some people. Let's continue this though. I want to make sure we kind of go through this together because this kind of gets a little weird. So n would be the total amount of trials. That's 5 free throws. 0.80 would be the probability of success, right? Because the number of makes is what our success is. So we have our n and p. If I was to write this as our binomial notation, it would be b comma 5 comma 0.80, meaning our binomial distribution had 5 total free throws with 0.80 as our probability. So as we approach this, what we want to do here is have our formula, which is NCR. We talked about this. You're all even write this down. This is our formula NCR, and this is going to be multiplied by p to the k power, which is the amount of makes that are there, times 1 minus p to the n minus k power. Okay? And this right here, the second part, would be the amount of failure here, and this is the success, and then these are all the combinations that result from that. Okay? So let's take a look at this real quick. So we have NCR, so we have 5C, and really the R, this should be K, I'm sorry. On your formula sheet, it's K. I've always looked at that differently from other math classes, but we'll do 5C1, okay? 5C1. And then this is going to be multiplied by the probability of success is 0.80 to the K power, which would be 1. And failure would be 1 minus 0.80 to the n minus k. So n minus k would be 5 minus 1, which would be 4. So if I was to rewrite this, I would put 5c1, which if I rewrote it, I could just put 5 over 1, right? 5, choose 1. And then I would multiply 0.8 to the first, or just 0.8, it's fine. 1 minus 0.8 is 0.2, that's failure. Okay, that's if I miss. And that will be to the fourth. Okay? And once I distribute this, the probability that I would hit one free throw would be, I could expect that to be 0.0064. So if someone says, oh man, I'm an 80% free throw shooter, let's say Matthew Wong, aka Beyonce, said, I'm an 80% free throw shooter and he only made 1, the probability that that actually would happen, seems that he's an 80% free throw shooter, would be 0.0064, okay? Now let's talk about the next one, and I'll clear this. Let's talk about 2. This would then be 5 choose 2, meaning 5 C2 here, okay? All right. We would then have success as 0.80 to the K power, which would be 2. Failure would be 0.2 to the N minus K, which would be 3, okay? When I plug that in and I solve that, again, all I'm looking for is recognizing it. That the probability of hitting only 2 out of 5 free throws would be 0.0512. So that's very possible that I could only hit 2, seeing that I was an 80% free throw shooter. So with that all being said, example 3 is kind of the big part that I want to hit on here. The fact that N is independent trials, again, this is our binomial distribution that's here to find the binomial, what we call binomial coefficient right here. What we want to do here is we know that N is N, P is P, right? This doesn't actually give us an example here. We're just throwing down the formula. That means that this would be, for 1, would be N over 1, because it's N over K, multiplied by P to the K power, and 1 minus P to the N minus K power. Got me? And so what we have now is this formula that's here to where whether it's 2, whether it's K, does not matter. If I did 2, the only difference is it would be N, like 5 total free throws up. If I make 2, that's what we did earlier. The probability of success here is P to the K, which would be 2 free throws made, multiplied by 1 minus P to the N minus K power. Got me? And again, where in this example, 2 would go in 4. Okay, so 2 would go here, here, and here. Okay? Excellent. Now, what I'd like for you to do is this, just for tomorrow, just to get kind of some practice on some of this stuff, I want you to see, are these binomial? Yes or no? Okay? All right, can we use a binomial random variable to distinguish this? And if so, just put yes, and if not, tell me out of the bins. If you say no, tell me out of bins what was wrong with it. Was it not binary? Was it not independent? Was it not a set number? Was there not a set success rate that was consistent there? So I want you to identify that, and then we'll go from there. And these right here are the answers, so if you want to go back to them, you absolutely can. And go from there if you want another practice here. Tomorrow we're going to go a little bit more into this binomial and geometric random variables here. This is another one that I want to look at just as to begin for tomorrow. Suppose a basketball player shoots 5 free throws. He's an 80% free throw shooter. Shots are independent of each other. Let X be the number of makes. Let's check bins. Is it binary? Yes, it is, because it's either a make or it's a miss, right? They say it's independent, and we assume it's independent because one shot's not affected by the other. We have a set number of trials, which is 5, and the success rate is 80%, and it's consistent, so we can use our binomial distribution here. So we're going to actually set this up as follows. So I want you just to put this here. This is the value of X. Down below, this is the probability of X. So how many makes can we have? Well, we can have 0, 1, 2, 3, 4, and 5, right? Okay, so we can do that. How do we do this? Well, each of these, remember from yesterday, or really from today because it's the same podcast, we remember that in each of these, we can do 5 because there's a 5, which is n, C, 0, okay? And then we would say the probability of success is 0.8 to the 0 power times the failure, 0.2 to the n minus k, which would be 5, because 5 and 0 have to add up to be equal to whatever my n was, okay? Which again was a 5 there. And once I do that, I get 0.00032, okay? Again, just make sure you recognize this. That's a huge thing. For 1, the only difference now is once I plug this back in, the 0 will turn into 1, and then this last one will turn into 4. And once I do that, I would get, and I think I did this just a second ago, I get 0.0064, right? Once I do 2, again, the same thing. This now becomes 2, and it changes these around. We get 0.0512. I think we just did that the other on the other slide there. 3 would be 0.2048. 4 should be the highest, right? Because 80% would be 4 out of 5. That should make sense there. 0.4096. And for 5, we would get 0.3297. Okay? Now with this, we have, this is a little different because now we're doing a binomial, right? But because this is a probability distribution, okay? What is the probability of getting a 3 or a 2, right? This is the probability of X being 2. What's the probability of X being 3? Probability of X being 4. Probability of X equaling 5. And so on and so forth, right? X equals 1. And probability of X equals 0, right? We know that these are the probabilities listed below. All 5 of these, or 6 because of 0. All 6 must add up to be equal to a probability of 1. Because of this is a probability distribution. Binomial probability distribution. What we do in our calculator is we can go to binom PDF. Okay? We can actually solve this by doing our binomial PDF. All right? It assigns a probability, because it's a probability PDF, the probability for each thing occurring. For instance, if I chose 5 starbursts, right? This 5 would represent the probability that I would choose 5 reds if I had a sample or a trial size of 5 with a probability of 80%, right? Same thing's true for this free throw. What's the probability that I will hit all 5 free throws? Well, this right here would be, the probability would be 0.3297. Now, we could do this by going to this formula, and we told you yesterday that you can recognize that and go from there. But it's much easier if we approach it by saying binom PDF, comma, n comma p comma k. Okay? Or n comma p comma x. Okay? All right? So that's how we would approach this or do this one. We will look at this on the calculator tomorrow. This is where we're headed. So just to give you a heads up on this, again, hopefully this was helpful for you to go in. Just to get the blanks down below, the histogram that you made, if I made a histogram here, okay, if I made a histogram, what I would get would be, let me actually move this here. The histogram, okay, this would be like all the way to 1, right, from 0 to 1. And I could say like this is 0.5 right here. And we would say that the amount of 0 to 1, 1 to 2, right? Actually, I would do this as 0. So 0 to 1. Oh, I'm sorry. Let's do this. To 1, 2, 3, 4, 5, 6. There is no 6, so we just stop there. So from 0 to 1, we would have a 0.0032, so that'd be here, right? Okay? All right, so we know this quantitative histogram here, okay? 1 to 2 would be 0.0064, so that's just a little bit above. 2 to 3, 2 would be, from our 2 here, would be 0.0512, so we would say 0.0 would be just, just slightly above. 3 to 4 would be 0.2848, so we're going to say 0.28 would be right here. 4 to 5 would be 0.4096, so that's going to be above that here. And 5 would be 0.32, so it should be about right here. So this histogram we made in part A is called a probability distribution function. Okay. So the way the probabilities are distributed. Good. All right. Or we could Joe, hold up. Make sure I get my or I'm sorry, PDF. Okay. We talked about that right up here. PDF. It assigns a probability to each value of x, and the calculator command for this is binom PDF, comma n, or n comma p comma x. And x represents the number associated to it. On the previous one, we used k as well, but that's what we're looking for. So the amount of numbers like a free throws made, right? So if I did binom PDF of, let's say, 3 makes, right? If I'm an 80% free throw shooter, I would put 5, comma, probability would be 0.8, comma, 3. And once I plug that in, it would get me 0.2848. Probability that I would hit 3 in that instance. Hey, I hope this was helpful for you. I know we went pretty deep into that, and appreciate all y'all do. Thank you for your hard work. We will see you soon. Bye now.